So now we're going to look at how to perform the exact same operations, but not carry these entire equations around. Here's our system of linear equations. And what we're going to show is that instead we can think of this as a matrix to which a right-hand side has been appended. And where does the matrix come from? Well, you can recognize this right here as a matrix vector multiplication, or the result of a matrix vector multiplication. So, we still have our same fundamental facts, and we're still going to reduce the system of linear equations to an upper triangular system. However, we're going to instead work with this appended matrix, which we're going to reduce to upper triangular form. So where does this all come from? Well, previously we saw how to take multiples of equations, subtract them off of other equations, in order to reduce the system of linear equations to an upper triangular system of linear equations. Now notice that all of the computation happens with the coefficients. So here I'm hiding the variables in gray. You may not even be able to see them all that well in the video. And the important thing is that it's the coefficients that matter, because it's the coefficients with which we compute. And as long as we keep those coefficients in a place so that we can recognize with which variable they should have been multiplied, we're going to be okay. As a matter of fact, we're going to make those variables disappear altogether. And when you do that, you end up with what they're called appended matrices. So these are matrices. We should have put parentheses around them. And then what you can do is you can say, look, I can still mimic exactly what I did before, which was to take multiples of the first row and to subtract those off of the second and third row. I can still compute my multipliers in exactly the same way as I did before. And then after one step, I will eliminate all of these coefficients right here, and we can either write the zeros there or leave them out altogether. And then in the next step, we look at these coefficients right here. We compute the multiplier by taking minus 16 divided by minus 10. And then we eliminate this coefficient right there. And then what we have here simply represents our upper triangular system of equations. So we can then do our back substitution exactly as we did it before, where all we need to do is recognize that this right here really represents that equation. This second row of coefficients really represents this linear equation, and this first row of coefficients really represents this equation right here. And then, of course, just as before, you really should go and check your solution. Now what we have is still a systematic way for transforming a linear system into an upper triangular linear system. We do so still because upper triangular systems are easier to solve. However, we now represent the equations as appended matrices, and we compute with these appended matrices. And the primary benefit is that it just requires a lot less writing, so you can get the job done much quicker. But you can also recognize that it should be easier to implement, because storing only the coefficients means that you create an array of numbers, and then you just manipulate that two-dimensional array of numbers.